Hello, welcome to this video. So on the previous video, we looked at density matrices as ways to describe the state of a system made up of lots of kind of bits or lots of subsystems. For example, we talked about using a density matrix to describe a mug with a drink. Because the mug and the drink form one system as a whole, like when you're drinking a mug of coffee, you don't ask for a mug and then separately a kind of floating ball of hot coffee. You want the coffee in the mug, so the mug and the coffee is one system together. And you describe the state of that kind of composite system using density matrices. And that's how I introduced density matrices as a way to describe composite systems. And that's really important if you're looking at things like entanglement, where you're looking at particular kind of correlations in quantum mechanics between kind of parts of the subsystem. However, there is a subtle use of density matrices even when we're not concerned with subsystems, and this refers to the question of Schrodinger's cat. Now, Schrodinger's cat is really about the fact that, according to quantum mechanics, an object should, when unobserved, enter a quantum state, that is a superposition between its possible classical states. However, this doesn't seem to happen with macroscopic objects like cats. Because, for example, if we put a cat in a box, and in this box we have a radioactive source. Now, due to quantum mechanics, it's entirely random when this source will emit a bit of radioactive radiation. That is, there is no, according to quantum mechanics, physical laws that can tell us exactly when this would happen. It's just a completely random process. But the rules is, whenever the source decays, it kind of triggers something that causes in some way poison to be released and will almost immediately kill the cat. Then this cat is trapped in the box. And then we ask, well, whilst the cat's in the box, what state is the cat in? Is the cat dead? Is it alive? How does that change over time? And the bizarre thing is, according to laws of quantum mechanics, it would seem at first that the cat would have to enter into a quantum superposition of being dead and alive, because due to our experiment there are no physical laws telling us whether the cat is alive or is dead. There's a non-zero probability that we'll find the cat as dead and a non-zero probability we'll find it as alive. So according to the rules of quantum mechanics, the cat should enter a quantum superposition state and be in some bizarre manner a mixture of both being dead and alive. And this idea that a macroscopic object should enter a quantum superposition state seems absurd, because I think I can speak for the whole of humanity when I say that none of us have ever observed a cat that is in a superposition state of being dead and alive. I don't think we really have an idea what that would physically look like. So this clearly and thankfully for cats doesn't happen, and not just for cats, it doesn't happen for humans. In fact, no macroscopic object seems to, at least for any reasonable length of time, exist in a quantum superposition state. And this fact seemed to be somewhat so contradictory to quantum mechanics at the start that this idea of Schrodinger's cat and a cat in a quantum superposition state was put forward as almost a very academic joke. It was made to explain how absurd quantum mechanics is and to suggest that there must be something fundamentally wrong with the theory. However, as it developed, it became more sophisticated. We began to develop tools like density matrices to describe the state of the system, and then we started to explore a phenomenon called decoherence. And it turns out decoherence actually explains why there are no Schrodinger's cats. That is why a cat will always either be dead or alive and will not enter a quantum superposition, at least for any physically sensible length of time of being dead and alive. So that's what decoherence is. So this is going to be a video on decoherence. It's worth saying this video might be slightly long. Hopefully it will be, at least below an hour, which might sound long. It's worth saying, most sessions at uni when you're learning something is an hour, and if you get a very enthusiastic lecturer, it might be 2 hours. So hopefully an hour isn't too long, and there'll be plenty of diagrams along the way to help us. Now, an important thing to note for this video is because I'll be trying to essentially prove that decoherence would result in us never having to describe a cat as being dead and alive in some strange quantum superposition. Because I'll be trying to kind of prove that, and we'll be talking about a mathematical process of decoherence, this video is going to be slightly more mathematically technical than my other videos. But that's really just this video. Most of my videos are less technical, however even here I will do my best to use as many diagrams as possible, and I will always be describing the physical meaning of the maths, so you won't have to follow along with very complicated mathematics. But it will be a bit more technical than my last video, and I will also be putting the equations on the screen to help those of you that would like to see the maths, the kind of equations at the core of this discussion. So we're going to start with a review of density matrices and how density matrices describe a composite system. Then we're going to move on to talking about density matrices in the case where we haven't got a composite system, but it's nice and classical. Then we'll be talking about mixed classical states before moving on to using density matrices to talk about how quantum states evolve and therefore being able to describe decoherence. And then we'll be using the mixed state anyway at the end, because as a special prelude to where we're going, it would turn out that a quantum system describing a macroscopic object will quickly decay into a mixed classical state. And it's because we'll be needing mixed classical states, we'll be needing to describe the state of a single system using density matrices instead of state vectors. But anyway, I'm getting a bit ahead of myself. For now, that's a review of the density matrix, and I'm going to be talking about it in terms of composite systems for this slide, because that's how I introduced it before, and that is its main use, and it will get us give us a feeling for why the density matrix is a density matrix, and how matrices can correspond to states in quantum mechanics. So that's a very good place to begin. So in my previous video, I talked about the age-old question of what drink would you like? It's one of our favourite questions in Britain. Whatever time of year, we're always asking what drink, and because in Britain we're a fan of tea and coffee, even in the hottest, most sunny day, we are always asking guests, would you like tea or coffee? So naturally, for the possible drinks available, I've got tea or coffee, so a tea bag or a large jar of instant coffee. And let's say there were 2 mugs available, a large mug and a small mug, or at least it was meant to be a small mug, but because I was trying to make the picture clearly visible, they ended up looking the same size. But we've got 2 different mugs and 2 different drinks. And the question is, how many unique combinations of the mug and the drink are there, such that whatever drink I have in whatever mug, that mug of the drink will be represented somewhere in the states of the system, the state of the composite system. And because we've got 2 drinks and 2 mugs, there are 4 unique combinations. I could either be having tea in the large mug, tea in the small mug, coffee in the large mug, or coffee in the small mug. So there are 4 unique combinations, or if you like, 4 states from my overall system, or my composite system. And because each state refers to 2 subsystems, the mathematical object describing the state has 2 indices telling me where the component needs to go, and therefore it's natural to represent the overall state as a mathematical object with 2 indices, or in other words, a matrix. And because, the choice of the drink only refers to one bit of information, the choice of the drink, we don't describe that using a matrix, we describe it using a vector, and similar for the size of the mug. An important thing with this is we therefore can describe the state of a system as a matrix, and because this matrix refers to probability in the concepts of quantum mechanics, it's called a density matrix, relating back to the idea of probability density. So this kind of gives us one way where density matrices are rather special. Any state can be described, anything that you can describe as a state vector, you can describe as a density matrix, but density matrices can describe states that state vectors can't describe, such as states of composite systems. You can also use density matrix to describe mixed classical states, which is where we'll be going. So in the next part of this video, we'll talk about the density matrix for a classical state where we know the classical state the object is in other words, the density matrix for a pure classical state, and then we'll be talking about the density matrix of a mixed classical state. And we're doing that because it turns out decoherence will result in our quantum state turning into a mixed classical state. So that's where we'll be going in the first part of this video. So quickly, before we move on to the density matrix for a pure classical state, I'll be just talking briefly about mathematical notation of density matrices, because this video is a bit mathematically technical, but also a lot of literature does flip between 2 different types of talking about density matrix. So for those of you that are interested in exploring this topic further, it's worth just mentioning briefly 2 different ways of writing a density matrix, or writing an equation for it. So the first one is the idea that we just define a density matrix as the tensor product of state vectors, where that circle with the cross in the middle is essentially a density matrix. When I say a cross, it's really a time symbol. Sorry, it's not a density matrix. Sorry, what am I saying? It's a tensor product. And it's a tensor product because it produces something with more indices than the thing we're taking the tensor product between. So our vectors have 1 index, but our density matrix is 2, for example. However, defining the state of our system as the tensor product between 2 state vectors is a definition for the idea of kind of our overall system now being described using a mathematical object with 2 indices. It doesn't necessarily say that we have to describe that mathematical object in the form of a matrix. And it's also worth saying, we talked about the state vector of subsystems and bringing them together using the tensor product to find the states of the overall system, but we can also describe the state of a system in and of itself, that is a state of a single system, and not thinking of it as being made up of subsystems using density matrices. In this case, we just define the state to be the tensor product of the state vector with respect to the state vector. There's a single kind of state vector being involved because we're talking about the density matrix of a particular state of a system, and we're not worrying about that system as being made up of subsystems or anything like that. For example, we can consider the cat in the Schrodinger's cat thought experiment as a single system. And we can think of this state vector, well, we can think of the state as described by a density matrix instead of a state vector, and this is how you would work it out. But as we've seen, we can think of the density matrix as being represented as a genuine matrix, and one way to get the matrix between vectors is to actually multiply a column vector with a row vector. Using rules of matrix algebra, you will always then produce a matrix if you multiply them in the right order. And so a mathematical kind of operation that is equivalent to the tensor product is this kind of multiplication of a column vector with a row vector. And that's just another way of writing the density matrix. The difference is, whereas the top equation defines what it is legitimately in terms of a tensor product, the bottom equation gives us a way to express it as a matrix, but matrix is a very good way to express it, so we'll be sticking with that. But it's worth saying that in a lot of textbooks and things, they'll introduce the density matrix firstly as a tensor product, and then move on to thinking of it as this operation of multiplying a column state vector with a row state vector. But the two are kind of equivalent. One just explicitly says we should think about the density matrix as the matrix. The other one doesn't explicitly really say that, although it does justify that the matrix idea would work. So now we're going to move on to actually talking about the density matrix of a classical state, a pure classical state. So where we know the state of the system. So, going back to the idea, although this will generalise even if we're not thinking of composite systems, but going back to the idea of a density matrix describing a composite system, if we're describing a pure classical state using a density matrix, then there will only be one non-zero component in that density matrix. And that's because, for example, if I'm drinking coffee in a large mug, then by definition I can't be drinking coffee in a small mug. And so because of that, and we're insisting that the state can't be spread out somehow between classical states, when we're thinking of our system classically, the density matrix referring to a pure classical state will only have one non-zero component, referring to the classical state of the system. And here's another example justifying why this is. So if I'm drinking a small cup of tea, then by definition I am not drinking a large mug of coffee. So clearly, kind of in when we're describing a classical system, if we know the state and are able to write this known state, then our density matrix will only have one non-zero component, which does kind of make representing the state of a pure classical system using a density matrix as heavily, overcomplicated, slightly mathematically ridiculous and over the top and flamboyant. However, as we've said, the advantage with density matrices is we can do so much with them that extends far beyond just things like describing pure classical states. And in the next slide we'll look at mixed classical states, which is something that where kind of density matrices really start coming into their own, even when we're not looking at composite systems. So the idea of a mixed state refers to the idea that sometimes we don't know what state something is in. So really, a mixed classical state is a bit of a misnomer. We really should call it something else, like unknown mixtures of states or something, although that would be slightly long. But the idea of a mixed state is really where we don't know what states something is in. We know the states it could be in, so we do know something about it, but we don't know which one it is actually in. An example of that is kind of, say I had keys for my house and also my neighbour's house. And I walk out of the door and I hear jangling keys in my pocket, but I have a sudden moment of dread where I realise I've only got one pair of keys, and I don't know whether I'll be able to use those keys to get into my house, or whether I'll have to, or what I'll do. So then I kind of like put my hand in my pocket. So when I put my hand in my pocket, I don't yet know whether the keys belong to, whether they're keys from my house or my neighbour's house. And so because of that, the state of the keys is in something called a mixed classical state. It's classical because the keys aren't in some quantum superposition of referring to my house and my neighbour's house. No, the keys are genuinely either keys from my house or my neighbour's house, so they exist in a classical state. I just don't know which one. And so I would describe the state of the keys as a mixed state. And the way you calculate a mixed state is, as you kind of might guess, by adding the possible classical states together, but weighting them by the probability of finding the system in that particular classical state. Now, formally, it really boils down to the fact that the kind of average value we measure for an observable should be the statistical average of the possible values weighted by probability. So if you've done statistics, you'll be fairly familiar with that. It's essentially that if a particular state is more likely, then that will have a higher effect on our average than very unlikely states for our object to be in. That's the kind of idea. And it's this idea, when formalised mathematically, that justifies that we get the density matrix for the overall system by essentially taking the weighted sum of the density matrices referring to classical, it's not so pure classical states. And so we have this expression for the density matrix. And it's worth saying this does generalise to mixed quantum states as well, although we won't be going to mixed quantum states. We will be looking at quantum states, but not mixed ones. But as I said, decoherence will end up resulting in a mixed classical state, so it's worth spending a bit of time talking about them here. So the mixed classical state is the sum, the weighted sum, of the probability of finding my system in the kth classical state, and also the density matrix referring to that kth classical state. And as I say, the formal justification is about, the average for a value we might measure referring to that state, like say the average mass of a ball. If we didn't know the mass of the ball, but we had many kind of many we thought identical balls, and then we tried to take an average to measure the mass of the ball, the average would have to follow certain, statistical rules. I am being a bit vague there, but I don't want to really get too heavily into the mathematics. But this is how we would find the density matrix of a mixed classical state, and it's really about the idea of highly statistically likely classical states have much more influence over the overall state than very unlikely classical states. So we talked about mixed classical states. Now we're going to talk about using a density matrix to represent a quantum state. Now you might at first think, why use a density matrix when state vectors work so incredibly well? And really the reason boils down to the fact that we want to talk about decoherence. And decoherence will result in a mixed classical state. So we need to describe the evolution of something to a mixed classical state. And as we said, we can describe a mixed classical state as a matrix. It can be a matrix with more than one non-zero component because it's a mixed classical state. And so we want to start with something that is also a matrix describing a state. Hence, we want to start with describing our quantum state as a density matrix, not as a state vector. But as we said, we can construct a density matrix from the state vector. So as a reminder, the state vector for a quantum state lies somewhere between classical states, and due to evolution it's free to evolve between them. According to Schrödinger's equation, at least different classical states have different energies, otherwise it's a generalised form of Schrödinger's equation that will govern the evolution of this quantum state. And we have a pictorial demonstration of this quantum state, but we can also write it mathematically by thinking of the components of how much of this state lies along one classical state compared to another. So if our quantum state is an equal mixture of classical states, let's say tea and coffee, then the components referring to tea and the component referring to coffee will have the same size, hence the numbers are the same. And I've also wrote a factor 1 over the square root of 2, and that's to ensure that we will either find our drink when we measure it in the classical state of tea or in the classical state of coffee. But for all practical purposes of what we're doing, that factor doesn't really matter. It's important in calculations, but qualitatively it isn't very important really at all for what we're doing. The main point is that if we have an object described by a state vector and the object is in a quantum state, there will be more than one non-zero component because some of its state is smeared out over different classical states. If we had one non-zero component for our state vector, then the quantum state would just be a classical state. And because our quantum state contains more than one non-zero component, our density matrix will also have more than one non-zero component. It's worth saying in this slide we are looking at pure states, not mixed states. Because we are claiming when we write psi that we know the state. We know its quantum state. We are explicitly writing it down. So this is not a mixed state. So really summarising, we've got three important things. So firstly, if we have a classical pure state as a density matrix, there is one non-zero component. If we have a pure quantum state described as a density matrix, there is more than one non-zero component. And if we have a density matrix describing a classical mixed state, then there is also more than one non-zero component. So a natural question might be, well, okay, what really is the difference between a quantum state and a mixed classical state, given both density matrices have more than one non-zero component? So what really is the difference? And this, as I've kind of alluded to before, is about the idea of evolution and quantum states referring, whereas an object in a mixed classical state won't, and that's what I'll come on to in the next slide. And the idea of the evolution of quantum states is important because decoherence describes how that is interrupted and how that interruption results in a quantum state turning into a mixed classical state. So, as we mentioned, we're in this slide talking about the time evolution of a density matrix, and one that is referring to a pure quantum state. So, pure quantum states evolve, and this has to be reflected in the density matrix. An object in a mixed classical state won't, or at least it won't by virtue of being in a mixed classical state. And to give an example of this, let's go back to the keys in my pocket. So let's say I'm outside. I don't know where the keys in my pocket belong to my house or my neighbour's house. However, I know that when I leave the house, my keys won't start evolving and changing from referring to my house to referring to my neighbour's house. And that's very, very important because, say, when we go out for a run, say, listening to the Lord of the Rings Fellowship music, we hear that kind of music invigorate us and we lose track of time, we don't have to worry about our keys changing what house they're referring to. If they did do that, keys would not be very useful at all. So even if my keys are in a mixed classical state, because all that's really saying is they are in a classical state, I just don't know which one, my keys won't start evolving, their state won't actually change. What might change is when I measure them, what will change perhaps is my information about that state, but that state isn't fundamentally changing. If I leave with keys referring to my house, then they're always going to be referring to my house, and similarly with the neighbours. The keys aren't evolving. But quantum states do evolve, and an object in a quantum superposition state will evolve over time. And that's an important distinction between mixed classical states and quantum superposition. Often people can easily get those two confused, and the way that quantum mechanics is popularly generalized does often confuse mixed classical states with quantum superposition, but they are different. And one example is about how quantum states evolve. And there are other important distinctions, but that's the one we're really main concerned with. So an object in a quantum state will evolve over time. That is, the state vector will begin to rotate, and we can think of that as part of the state vector picking up a phase shift that kind of ends up resulting in the overall vector beginning to rotate. And really, because phase shifts are often described as multiplication by an object with size 1, so we don't squash or squeeze that component, but due to rotations it has to be a function that changes, and so we usually use a unit complex number, because it's a function always with size 1, but which can change over time. And therefore, because of that, we usually describe vectors in a complex plane, allowing us to talk about introducing phase shifts, where the phase shift is described using a unit complex number. Which does get sometimes quite unintuitive, but I wrote it here for example. So, because of Schrodinger's equation, one of our components picks up a phase shift, and the phase shift is described by the unit complex number e to the I omega t. Now, e to the I anything is a unit number. That is, it's a number with size 1 existing on the complex plane. And omega is telling us how fast this component is changing. So it's really telling us about how quickly our quantum state is evolving. And at least in the case of energy, if our two classical states have different energies, then the larger the difference in energy, the faster this evolution will happen. It also refers to the frequency of light that an object emits when it's in an energy superposition state. If it's a charged particle, that's in a superposition state anyway. That's going slightly off track. The main thing is, omega, this curly W, is really telling us how quickly this evolution is happening. And it's this evolution that makes quantum superposition states clearly distinct from mixed classical states. And if we want to represent the quantum state as a density matrix, then this time evolution enters also into the density matrix. And we end up with something like this, as can be found using the rules of matrix algebra by thinking of the density matrix as the column vector multiplied by the row vector, where the vector being our state vector here. Although exactly how we get those exact components doesn't really matter, what's important is that this evolution feeds into this density matrix. Now, before, we mentioned mixed classical states. In mixed classical states, the state doesn't have any natural dependency on time, unlike the density matrix for a quantum superposition state. And that's important for what we'll be coming on to now, where we'll be talking about decoherence. Now we've built up a way to describe a quantum state using a density matrix, and also we've discussed how density matrices can be used to describe mixed classical states. So we've now got to really the pinnacle of this video, so don't worry if you look at these equations or you're a little confused what's going on. What I'm going to do is explain what's happening with these equations, and explain how an object in quantum state will quickly enter into a mixed classical state if it interacts with its environment regularly, like macroscopic objects such as cats. The equations are here just for those of you that are mathematically inclined to follow along with me as I'm talking and to see it explicitly written. Let's say, as I mentioned before, when we're talking decoherence, we're really talking about a macroscopic object, like a cat or something like that. So macroscopic objects are made up of an unbelievable number of particles, many of which are interacting with an external environment. And what that means is, at least in terms of quantum mechanics, it's a really bad idea to consider a macroscopic object as being isolated from the environment. In fact, it's kind of quite unphysical. I mean, if you think of a cat, the number of molecules of the gas around it in the air it's interacting with every second is unbelievable, and even if we would put that cat in space, it would still be interacting with radiation from the sun, and even if we made it into deep outer space, it would still be interacting with virtual particles. So we can't really ever cause a macroscopic object to, for any reasonable length of time, be well approximated as a closed system that is interacting with the environment, at least as far as quantum mechanics is concerned. And because of that, things like cats are constantly interacting with their environment, and this interaction is interrupting this quantum evolution. Because every time a quantum object is observed, it collapses into existing in one of the classical states, and this collapse keeps happening again and again. And because quantum mechanics is random, every interaction resulting in a collapse happens with a probabilistic outcome, so we don't know what state the quantum mechanical state vector will collapse into. And because this is happening so frequently, really, the general state we actually see of a macroscopic object is actually a statistical mixture of the classical states we can find it in. And what that results in is this phase factor forcing this state to evolve over the complex plane to be averaged out over all its possible values. Now we can think of all possible kind of outputs of the unit complex number as being on the circumference of a circle in the complex plane centered at the origin. And if we think about averaging over all points on the circumference and ask, well, what's the average point? Well, because all points are equidistant from the centre of the circle, and the circle is completely symmetrical, the average displacement is zero. That is, the average of all those points is the very origin of our coordinate system. And so what that means is, due to regular interactions of a macroscopic object with the environment, very quickly this kind of coherent factor, this factor corresponding to the natural quantum evolution, goes away, and its amplitude drops very sharp, and very quickly it becomes, to all practical purposes, zero. It almost completely vanishes. And it's this process called decoherence, and we often mathematically model decoherence as essentially damping down the oscillations, damping down this natural quantum evolution by an exponential factor, because we like exponential factors in physics. And exponential factors do damp it down very, very quickly indeed. And there are other reasons to use exponential factors as well, including the idea of this drop slowing down over time. But the key thing is, very quickly this the coherent factor just seems to vanish. And so before, whereas we had a quantum state that was evolving with time, when we take account of decoherence, there's added to the I omega t, there's a minus gamma t, and gamma is a real number, so the minus gamma t refers to exponential decay, and gamma really tells us how quickly this damping of the oscillation term is occurring, so how quickly decoherence, or how strong the decoherence is. And what then happens is, over time, and technically as t goes to infinity, but for practical purposes to a very good approximation in a very short amount of time, the off-diagonal components of our density matrix, or the terms that refer to the evolution of our quantum state, go to zero. Now you might realise that then we're left with a density matrix with more than one non-zero component. So from that we can go, well, it could be a mixed classical state, or it could be a quantum superposition state. But we've also, in our middle equation, not only have we got more than one non-zero component, but the components don't change with time at all, so it's a time-independent density matrix, which, as we said, means it's not going to refer to a quantum superposition. So in other words, we end up with a mixed classical state. And so decoherence causes, by this damping of the coherent terms, our quantum state to turn in very quickly into a mixed classical state. And in the bottom equation, I've broken down the density matrix describing this mixed classical state into its kind of viable classical states, when you can see each density matrix in the bottom equation only has one non-zero component, hence refers to a pure classical state. So this kind of process explains really why there's no such thing as a cat that's dead and alive, or at least if a cat enters that quantum superposition, due to it being macroscopic and interacting with the environment, this superposition is very, very quickly destroyed. And we have to use density matrices to model this, because what the state ends up turning into is a mixed classical state, which, as we mentioned, we can't represent states using state vectors, because by definition state vectors are us declaring what the state is, whereas density matrices can describe mixed states, using the idea of finding the statistical average of the classical pure state density matrices. And you might ask, well, why can't we do a similar thing with state vectors? Well, if we did that, then we would be unable to distinguish between a quantum superposition and a classical mixture of states, and we'd have to be able to distinguish between them because they evolve differently, as we mentioned. So this has been a very light-hearted, might not feel like that, but to compare to a really, really formal overview, it is a very light-hearted overview of decoherence and why Schrodinger's cat is not found in nature. So I put our conclusion here. I'm not gonna kind of like read it out because we've already really said it, and there's a lovely cute picture of a cat. I really love cats, so I'm personally very glad that decoherence happens, so I will never observe my cat Arwen waking me up in the morning being both dead and alive, which I am very grateful for, because I might have a heart attack if I found her both dead and alive, although to be honest I would be so confused I might just call the doctor to work out what's happening. But anyway, so, thankfully for us, fans of cats, decoherence exists. And it's decoherence that really prevents macroscopic objects being stable quantum superposition states. Even though quantum superposition states are very stable for atoms and subatomic particles, where interactions with the environment is nowhere near as significant or as frequent. So this has kind of been a summary, and if you enjoyed this video, consider hitting the like button or sharing it if you would like. That helps these kinds of videos be seen by more people and helps share the wonders of quantum mechanics in a hopefully approachable way with as many people as possible, because the universe is an amazing place, and it's important that kind of like people get to see kind of certain secrets that physics reveals about the universe. And I hope this video has been fun. Apologies that this video has been quite long. I mean, looking at the time and the length of this video, it has been quite long. But hopefully it hasn't felt too long, and it is under an hour anyway. So yeah, that's it's under the length of a typical kind of like session, if you like. But anyway, as it's been a very long video, I'll leave it there. I wish you a really good week. Remember to enjoy the sun. Don't spend too long on YouTube. And I wish you a really good week ahead.